Let us now look at multiplication using the shift and add process. And here is an example. 1011, that is decimal 11. That is our number A, A3, A2, A1, A0. A3 is this and A0 is this one. So A0 is the LSB, A3 is the MSB. Here is our number B, and that is decimal 13, and we want to multiply these two. So this is our multiplicand and this is our multiplier. Alright, where do we begin? We look at the LSB, that is 1. So we multiply the multiplicand by the LSB, and in this case it means we just reproduce this number as it is, 1011. Next we look at the next higher bit, and that is 0, and when we multiply the multiplicand by 0 we get 0 0 0 0, and that is what we write over here, and we have to shift it left because that gets a higher weight, so therefore there is a 0 coming in from the right here. Now a comment about the notation. This Z is actually the same as 0, but we use a different symbol Z to denote zeros which are independent of the numbers being multiplied. So this Z is always going to be 0 no matter what these numbers are. After that we add these two numbers, and that is the result. Next we look at the next higher bit, that is 1, so we reproduce the multiplicand, and now we shift it left 2 times, and therefore we get these two zeros here. We add again, then we look at the last bit, the MSB, that is 1, therefore we reproduce this multiplicand again like that and shift it 3 times, so we get these 3 zeros here, and then finally we add these two numbers to get our final product, and that is decimal 143. Let us see how this method can be implemented. We start with two registers, 4-bit registers, register 2 and register 1. This is going to be our LSB, that is going to be our MSB, and we initialize both these registers with all zeros. Alright, now step number 1 is to load 1011, the multiplicand, this one, in this other register, since B0 is 1, and now we are going to add these two 4-bit binary numbers to get this result here, and this binary number is simply going to be copied to this part. Alright, so we have got 1011. In this case, of course, these are all zeros, so we have the same number over here. That is the result of the addition. Next we shift this result right by 1 position, so this number 1011 has appeared here now, 1011, and 10 has got padded from the left. Alright, now the next bit, since B1 is 0, we load 0 0 0 0. We are talking about this step now, and now we are going to add these two numbers, and now you see that this corresponds to adding these two numbers here, and this one is going to get added to this 0. That is anyway happening because this one is simply going to get copied over there. Alright, so that is the result of this addition, and we keep repeating this process until we reach B3. So next step, shift right 1 bit, so this 0 1 0 1 1 has come here, 0 1 0 1 1, 1 0 has got padded from the left. Now we load 1011, since B2 is 1, that corresponds to this step here, add, shift right, and finally we load 1011 because B3 is equal to 1, that is this step here, and then add and shift. So that is our final result, and that is indeed the same as this number here. Let us look at this circuit and try to figure out what it is doing. We have 4 JK flip-flops and they're all positive edge triggered. Here is the direct set input SD. This is the direct reset input RD. And what we notice is that although we are using JK flip-flops here, we are really using them as D flip-flops, because you see that J and K are inverse of each other in each of these cases. We have 0 here, 1 here, we have Q3 here, Q3 bar here, Q2 here, Q2 bar here, Q1 here, and Q1 bar here. So although these flip-flops are JK flip-flops, the functionality is like that of a D flip-flop. So essentially it's a shift register that we are talking about. Alright, now let us look at the connections. The clock is common to all of them, and the clear input is also common, that is going to the direct reset input of each flip-flop. Now to SD we are connecting this variable called load and it with some other variable here. That variable is A3 here, A2 here, A1 here, A0 here. And A3, A2, A1, A0 represents a binary number, and what we are going to do is to load this binary number into these flip-flops to begin with. These are the signals being applied. A single pulse here for the clear signal, single pulse for the load signal, and this clock signal has been derived from a free running clock and some logic. So the first pulse starts here and there are a total of 4 clock pulses. Alright, now let us see how this works. At this time we have load equal to 0, so the output of this AND gate is 0 and so are the others. So therefore SD is 0. The clear input is high, so therefore RD is 1. So we have SD equal to 0 and RD equal to 1, and that will clear the flip-flop. That means Q3 will be made equal to 0, Q2, Q1, Q0 will also be made equal to 0. After the clear pulse, the load pulse comes along, and let us look at the situation somewhere here. So the load signal is 1, clear is 0. So all the RD inputs are 0 now. This is 1, so the output of this gate, that is SD for this flip-flop, is equal to A3. Now let us take two situations, A3 equal to 0 first. So that means we have SD equal to 0 and RD equal to 0. So nothing is really going to happen. The flip-flop will work normally. Its output, if you recall, is already 0, and since there is no clock edge yet, the output will continue to be 0. So that is the situation if A3 was 0. Now consider A3 to be 1. In that case SD will be 1 and RD is 0. So therefore the flip-flop output Q3 will get set to 1. In other words, if A3 is 0, then Q3 would be 0 at this time, and if A3 was 1, then Q3 would be 1. So this bit here is simply getting loaded into this flip-flop, and similarly A2 will get loaded here, etc. So this entire binary number has now got loaded into this shift register. Alright, now the clock pulses come along. What happens when the first active edge comes? This 0 will get transferred to Q3. Whatever Q3 was will go to Q2 and so on. So that's a shift right operation by one position. And with each additional active edge, the data will simply shift right one more time. So that is how this circuit works. To summarize, all flip-flops are cleared in the beginning with RD equal to clear equal to 1, this part, and SD equal to 0. When load is equal to 1, this part, ST equal to AI, that means A3 or A2 or A1 or A0, and RD is 0, that means the binary number gets loaded into the shift register. And subsequently, with every clock pulse, the data shifts right and appears serially at the output Q0 over there. So first this A0 will appear at Q0, and after that this A1, which has got loaded in this flip-flop initially, will appear at Q0, and so on. And this corresponds to parallel in serial out data movement. Let us now look at this schematic picture showing this parallel in serial out data movement. What is parallel in? This is our data A3, A2, A1, A0, and that is getting loaded parallelly into these flip-flops like that. Alright, so that happens in this phase, and now the clock pulse comes along, the first clock pulse. We're going to have a shift right operation. Because of that, a 0 appears in the first flip-flop because we have J equal to 0 here, and whatever was here gets shifted to the next flip-flop, and so on. With one more clock pulse, we have one more shift right, and so on.